We have seen in the previous video how we obtain the integration of the electric flux density over a closed surface for infinitesimal volume structure, and we proved that for the case of the electric flux density D, the integration over a closed surface d dot ds was the derivative dx with respect to x, dy with respect to y, dz with respect to z, multiplied by delta. Okay, now we are going to study this differential operator on a general vector, say A. So for a general vector A, the derivative of ax with respect to x plus the derivative with ay with respect to y plus the derivative az with respect to z equals the limit when delta v tends to 0 of the integration over a closed surface of this vector A dot the closed surface over the incremental volume V. Effectively, this operation is called the divergence of the vector A, and it can be abbreviated as div A. The divergence of vector flux density A represents the outflow of the flux from a small closed surface per unit volume as the volume shrinks to 0. If we have positive divergence, this means that the vector quantity indicates a source. So we have positive charge density inside this infinitesimal volume. So the flux is going outside the volume. So in this case, we are talking about a source or flux emitting from this closed surface. On the other hand, if we have negative divergence, it means a sink, or in other words, a negative charge. So the electric flux enters inside the volume, not going outside the volume. It should be noted that the divergence is an operation which is performed in vector quantity. So the divergence is performed in a vector quantity. But the result itself is a scalar quantity. So it should be noted that the divergence is an operation which is performed in vector, but the result is scalar quantity. And the divergence tells us how much flux is leaving a small volume or per unit volume, uh, and no direction is associated with it. Effectively, the direction is associated with the positive or negative. If it is positive, the flux is going outside the surface. Is negative, the flux is going inside the surface. But which direction, rho, r, x, z, doesn't matter. Okay? So we are going to define this differential operator as the divergence. And effectively, this differential operator here is represented in Cartesian coordinates. As an example, it is required to find out approximate value for the total charge enclosed in an incremental volume. The volume is 10 to the power minus 9 meter cube located at the origin. Located at the origin means that the value of x0, y0, z0. If the value of d, or the electric flux density d, equals e to the power minus x sine y in x direction minus e to the power minus x cosine y in y direction plus 2z in the z direction, coulomb per meter square. According to Gauss law, we say that the integration over a closed surface d dot ds equals the charge included. But here we don't have the included the surface. We have the volume. So instead of going from the integral form of Gauss law, we can say that the divergence of d would equal rho v. nabla dot d equals rho v. And rho v multiplied by delta v would equal the charge included. So we can calculate it by nabla dot d equals rho v and multiply rho v by delta volume. Okay? Nabla dot d, or the divergence of d, is the derivative of dx with respect to x plus the derivative of dy with respect to y plus the derivative of dz with respect to z. So we are going to differentiate the dx component with respect to x. The differentiation of dx, here sin y is constant with respect to x, so e to the power minus x, if I differentiate it, it would be minus e to the power minus x. So the differentiation of dx with respect to x would be minus e to the power minus x sin y. Now the differentiation of dy with respect to y. dy is minus e to the power minus x cosine y. So e to the power minus x is constant with respect to y, but cosine y can be differentiated with respect to y. So cosine y, its differentiation would be minus sine y. So minus minus, it would be positive e to the power minus x sine y. And finally, the differentiation of dz with respect to z, this dz, 2z, differentiated with respect to z, it would be 2. Summing these parts together, we find out the divergence of d, or nabla dot d. So this is the value of nabla dot d. This actually is the divergence of the electric flux density, which equals the volume charge density as a function of x, y, and z. Now, it is required to find out the volume charge density at the origin. So, at the origin, we are going to apply x0, y0, and z0. So, if we apply x0 here, e to the power 0 is 1, sine 0, so sine 0 is 0, so this term is 0. Similarly, this term is 0 too, because sine y. And finally, this term is 2, it is constant. So, the value of the divergence of the electric flux density at the origin would be 2. This actually equals the volume charge density at this point. If we multiply this volume charge density by delta V, we can find out the total charge. So the volume charge density 2, because these are zeros, 2 multiplied by delta V, which is 10 to the power minus 9. So we are talking about 2 multiplied by 10 to the power minus 9. We are talking about 2 nanocoulombs. So that's what we are seeing here. At the origin, the first two terms are 0 because sine y, and the last is constant 2. Thus we have the charge enclosed in a small volume element. There must be approximated as 2 multiplied by delta V, and we have delta V 10 to the power minus 9, so we are talking about 2 nanocoulomb. Okay? Alright. Now let us go back to Gauss law in differential form, or first Maxwell equation. We said that nabla dot d equals rho v, or it can be read as the divergence of d would equal rho v, or it can be read as the divergence of the electric flux density equals the volume charge density. All of them are the same. So div d equal rho v, and the integral form of Gauss law, it was the integration over a closed surface d dot ds equals the charge included inside the surface q. And effectively q, it can be obtained as the integration of the volume charge density dV. So, in other words, we can say that instead of rho v, we can replace rho v by the divergence of d. So, this would equal the integration over the volume div d multiplied by dv. By taking the two extremes of this equation, we can conclude that the integration over a closed surface of d dot ds equals the integration over the volume, the divergence of d dv. And effectively, we have proved this rule for the electric flux density, but effectively this rule is valid for any vector quantity. So this rule is known as the divergence theorem. The divergence theorem states that the integral of the normal component of any vector field over a closed surface is equal to the integral of the divergence of this vector through the volume enclosed by this closed surface. The integral of the normal component, which is related to the dot product, the integral of the normal component of any vector field over a closed surface equals to the integral of the divergence of this vector through the volume enclosed by this surface. This is known as the divergence theorem. Effectively, we have studied the divergence till now in Cartesian coordinates and said that the divergence of d is the derivative of dx component with respect to x plus the derivative of dy component with respect to y plus the derivative of dz component with respect to z. What will be the situation in cylindrical and spherical coordinates? In cylindrical coordinates, the divergence of d is 1 over rho multiplied by the derivative with respect to rho, rho d rho. Take care, in this case, we have the rho component of the electric flux density. We first multiply it by rho, and after multiplying it by rho, we take the derivative of this component with respect to rho. And after taking the derivative, we divide this by rho. So no one says that we can take this rho with this rho. This is not right. Okay? We take the rho component of the electric flux density d rho at the beginning and multiply it by rho. And the result is derivative with respect to rho, and after taking the derivation, we divide it by rho. Plus 1 over rho, the derivative of d phi with respect to phi, plus the derivative of dz with respect to z. Effectively, this component corresponds to this component. As usual, in the relation between cylindrical and rectangular, the z component here is the same as the component. Alright? In spherical coordinates, the divergence of d is 1 over r squared multiplied by the derivative with respect to r, the value of r squared multiplied by dr. And the same what we have discussed here is the same here. Okay? Plus 1 over r sine theta, the derivative with respect to theta, sine theta multiplied by d theta. So at the beginning, we take the theta component of the electric flux density and multiply it by sine theta, and then we take the derivative of all this component with respect to theta, then we divide this derivative with respect to 1 over r sine theta. Alright? Plus 1 over r sine theta, the derivative of d phi with respect to phi. This is divergence with the divergence of d in spherical coordinates. As an example, it is required to evaluate both sides of divergence theorem for the field d equals 2xy in x direction plus x squared in y direction coulomb per meter squared, and the rectangular parallelopiped formed by the planes x equals 0 and 1, y equals 0 and 2, and then z equals 0 and 3. So this actually the limits of the differential or the infinitesimal differential volume element which we are going to apply. So effectively it is required to calculate the integration of d dot ds over the closed surface of this volume. Then it is required to evaluate the integration of the divergence of d over this volume, and it is required to prove that the integration over the closed surface of d dot ds equals the integration over the volume divergence d dv. Okay, so we are going to start with the integration over the closed surface. The closed surface, we have 6 faces here. The face at x equals 0, and the face at x equals 1, the face at y equals 0, and the face at y equals 2, the face at z equals 0, and the face at z equals 3. So the integration over a closed surface d dot ds would be 6 integration 1, 2, 3, 4. They should be 6. Okay, let us see why they are not 6. We are talking about, yeah, I understand. We have x component, y component, and we don't have z component. So effectively, the surface z equals 0 and the surface z equals 3, their normals are negative z and positive z. So in this case, the integration on the surface z equals 0 would be 0 because we don't have dz component. Similarly, the integration on the surface z equals 3 would be 0 because we don't have z component. Alright? So we are going to talk about the 4 surfaces: x equals 0, x equals 1, y equals 0, y equals 2. Alright? Now, the surface x equals 0. The surface x equals 0, its normal at the direction minus x because it corresponds to the back surface, the parallel. So it is in the back, so it is negative x. So the normal here in the negative x direction, and the area would be yz. So we are going to integrate along yz, and it is in the negative x direction, and the limit of integration on the y from 0 to 2, and the limit of integration on the z from 0 to 3, and the value of x at any point on this plane, x equals 0. So we are going to apply this value here. So x equals 0. So here 0 multiplied by ax. So d at x equals 0. So this value is 0. So effectively, this is surface, or the integration on this surface will be 0. Alright. The other face, x equal 1. At x equal 1, it is the front face, and in this case, the normal to the surface would be in the positive ax. And the surface would be composed of delta y, delta z. So the surface would be delta y, delta z in x direction, positive x direction, and the limit of integration on the y from 0 to 2 and on the z from 0 to 3. And the value of x in this case at any point is 1. So we are going to apply the value of d at x equal 1. Now we have completed the two phases for x equal 0 and x equal 1. We are going to the two phases y equal 0 and y equal 2. In the phase y equal 0, the normal would be in the negative y direction. And the phase y equal 2, the normal would be in the positive y direction. And in both cases, delta s would be delta x multiplied by delta z. So the phase y equals 0 would correspond delta x, delta z in negative y direction. And the limit of integration on the surface would be x from 0 to 1 and z from 0 to 3. Similarly, the plane y equal to would be dx, dz, and the normal at the plane y equal to would be in the y direction ay. The limit of integration would be from 0 to 1 in the x and from 0 to 3 in the z. And the value of y here is 2, the value of y here is 0. As we mentioned, we have two other phases, one at z equals 0 and the other at z equals 3. Here the normal in the negative z direction, here the normal in the positive z direction. But because the electric flux density doesn't have a component in z direction, so d dot ds in these two cases would be 0. So we will not write these two phases. Okay? Alright. Now we have 4 surfaces and 2 zero surfaces already. Let us apply the value of x equals 0 here. To apply x equals 0, so this value would be 0. So this would be completely 0. Now here x equal 1. I think this is repeated. So no, it is not repeated. We have taken the negative sign outside. Okay, we have taken the negative side outside. Now we are going to apply the value dx at x equals 0 is 0. dy at y equals 0. dy at y equals 0. Here dy at y equals 0. We apply 0 here, but there is no 0 here. So it is x squared ay. dy at y equal 2. Here we have this exponent, but the y component is x squared 2. So dy at y equals 0 equals dy at y equal 2. So in this case, we are going the first term dx at x equals 0 is 0. So this will be removed. dx at x equal 1 would be 2y multiplied by 1. 2y multiplied by 1 dy dz plus here dy negative plus dy positive, and because they are the same, so in this case the integration here would equal the integration here. So there is no need to make the integration because it is the same and they have different signs. So the summation of this integration minus this integration would be 0. So the only integration would be this one. Alright, so this is 2y dy dz, 2y dy dz. We make the integration along y from 0 to 2 and along z from 0 to 3. So this y squared, and we apply from 0 to 2, it would be 4 dz. So dz would be z from 0 to 3. So 4 multiplied by 3 would be 12. So the integration over the closed surface d dot ds in this case is obtained as 12. Let me remind you, it is required to find out the integration over the closed surface and the integration of the divergence of d on the volume. So we are going to make the divergence of d and integrate it on this volume from x 0 to 1, y 0 to 2, and z 0 to 3. And we see if it will equal the integration over the closed surface or not. Alright, here the result which we have obtained for the integration over the closed surface. The divergence of the d would equal the derivative of the x component with respect to x plus the derivative of the y component with respect to y plus the derivative of the z component, which is actually already 0 with respect to z. So the derivative of the x component with respect to x is 2y. The derivative of the y component with respect to y is 0 because x squared is constant with respect to y. So divergence d would be the derivative with respect to x 2xy plus the derivative with respect to y x squared, it would equal 2y. Now, if we are going to make the volume integration of delta v or the divergence of d with respect to the volume, so the divergence of d is 2y and the volume is dx dy dz, and the limit of the integration for the x from 0 to 1, from y from 0 to 2, for z from 0 to 3, we are going to make this integration. For x, it's okay, it is constant, so it would be 1. For y, it would be y squared, and the limits from 0 to 2, it would be 4. So it would be 4. For z, it would be constant, so it would be z, and the limits would be from 0 to 3. 4 multiplied by 3, it would be 12. 12, and previously we have obtained the same 12, so the integration over a closed surface d dot ds equals the integration over the volume divergence d dv, which is the divergence theorem. Okay, so these examples show us the divergence theorem is valid for both sides, so we can calculate it from the integration over closed surface or the integration over the volume for the divergence of the. Okay, alright. By this end, we have completed chapter 3 for Gauss law. In this chapter, we have studied Gauss law in integral form and in differential form. And we concluded that the integration of a closed surface of d dot ds, or in other words, the total flux from a closed surface equals the charge included inside the surface, which can be represented in differential form as the divergence of the electric flux density equals the volume charge density. Alright, next chapter we start with electrical potential. See you in the next chapter.